This is chapter 7 about deadlocks. Okay, so deadlocks means it's from the name you can have an idea. So they got some kind of blocks or kind of something is preventing from execution. That's the idea you can have it. So that's what you call here deadlock. So what does it mean is, for example, a process is moved to a waiting state. Okay, and it's waiting for some resources, but the resources is not never ever assigned to the process, so the process turned to be waiting and waiting and waiting because the resource is held by other process. The other process is not really releasing it. You get the idea? For example, I'm waiting for you to give me a pen. So I'm waiting and waiting, but you still use your pen and you're not giving me, and I'm not writing it. Can you get the idea? So that's the case of deadlock. Okay. So just I understand that a process requires the resources, and the resources are not available at that time. So the process goes to the waiting state, and the waiting process never again come back to the running state because the resource is not assigned to the process, because the resource is held by the other process. Other process keeps the resource and it's not releasing the resource. If the resource is released, the waiting process can take it and it start execute. You get the idea? So that's the basic idea of what deadlocks. Okay? It's all mentioned here. You see, in deadlock, process never finish execution because the system resources are tied up. Tied up means it's been used by some other. It's been using by some other process. Okay, so it prevents the other job to start executing. I mean to say the other job is still waiting and waiting and waiting for the resource. Okay, and the resource is tied up with other process. Somebody else is holding that resource. This process is still waiting and waiting. This is deadlock situation. Okay, so that's the idea of deadlock. Okay, so let's see the situation, why it arrives. So there are four conditions that's this is reason for the deadlock situations, which is mutual exclusion, hold and wait, and the two more is in the upcoming slide. Okay, so let's see the mutual exclusion. For example, mutual exclusion means like one resource is, for example, at least one resource must be held in a non-shareable mode. What do you mean by non-shareable is it can't be shared, something like that. So only one process at a time can use that resource. It can't be shared. Shared means at the same time everybody is accessing it. No. So pick one, at least one resource like a non-shareable. Non-shareable means at the same time not more than one process will be using it. Okay. So mean to say only one process at a time can use the resource. If another process requests the resource, the requesting process is delayed because it will be put into the waiting state until the resource is released by the process. You get the idea. What I'm trying to say is this is what you call mutual exclusion. Wait a second. Let's assume this is a process P1 and we have another process called P2. So there is a there is a non-shareable resource. Okay, for example, you have a resource and this is what you call R1. This resource, let's say it's a non-shareable. Non-shareable means only one process can use it at a time. Okay, it's not allowing more than one process to use at a time. So you have a non-shareable resource, and if one process, let's say this resource is assigned to P2. P2 is using this resource. See the arrow? This resource is assigned to P2. Okay, so if a process requests the resource, so you see the arrow is coming like that. This means one is requesting the resource. What happened to resource? This resource is already been used. I mean, it's being currently used by P2. So P1, it turns to be a waiting state. So P1 has to move to a waiting state. It waits and waits and waits until this resource is released by P2. This is what you call mutual exclusion. Okay, so here got a deadlock situation, is it? Okay, doesn't matter. Next one, hold and wait. For example, a process must be holding at least one or more whatever resources, waiting to acquire additional resource. See, let's see the same scenario. R1 is assigned to E2, and maybe it is R2 is also, maybe E2 contains more than one resource. I don't care, because they say here at least one. At least means at most any number. So P2 is currently executing with the resource R1 and with the resource R2, but P2 also need a resource R3, for example. For the completion of execution, see the arrow. The arrow goes like that, mean to say it is requesting R3. That is the meaning. If an arrow comes like that, R2 is given to P2. You see the arrow is different. So here you see the arrow, this arrow means it's going like that. So P1 is requesting R1. This is the meaning of this arrow. Okay. Just understand, because we will be using this type of diagram up in the upcoming slides. Okay, let's come back. P2 is currently executed by the CPU. P2 already given R1 resource, another resource R2, and for execution, to complete the execution, P2 wants one more resource called R3. Assume that R3 is given to somebody else. R3 is not free. It's assigned to somebody else. So what happens here? P2 will wait for R3. Where is R3? R3 is given to somebody else. So P2 will be moved to waiting state. When P2 is moved to waiting state, what happened to R1? And what happened to R2? The P2 still keep them. You get the idea? See, that's what we call hold and wait. It holds the R2 and R1 and it wait for the R3. So whoever wants R1, whoever needs R2, they have to wait also. P1 is, it needs R1. It can't be given R1 because P2 holds it. So P1, the process P1 is waiting and waiting. Process P2 holds something and waits for something. You get the idea? So this is about the hold and wait. Let's move on to two more situations. No preemption. You already heard about the word preemption. You know, in CPU scheduling, we already discussed the preemption, non-preemptive, priority scheduling, preemptive, priority scheduling, something like that. So this word preemptive is not new for you. This one, it's not new for you. Okay. Resources cannot be preempted. Preempted means released. Okay. That is, a resource can be released only voluntarily by the process holding it. After that process, complete the task. This was the case before I told you. Do you remember the previous slide? I told you that there is a process P2. P2 holds a resource, for example, R1. So this is holding a resource R1 and it is requesting another resource called R3, for example. So it is requesting this resource R3. So this resource R1 is assigned to P2, but when the resource will be released, when P2 finished execution. Until P2 finish execution, whatever resource P1 holds will not be released. Okay, can you get the idea? That is no preemption. Preemption is something called releasing. Okay, here just have the meaning releasing. Okay. So after the process completed the task only, the resources will be released by the process. So no preemption. Okay. The last one is circular wait. What does it mean, circular wait? It's very simple. You see everything in a circular manner. Okay. For example, I hold the pen of Luzan. Luzan hold the pen of Vejdan. Vejdan hold the pen of Kavita. So you see the circular one. You get the idea. I'm waiting for Luzan, and Luzan is waiting for Vejdan, and Vejdan is waiting for Kavita, and Kavita is waiting for Luzan. No, there is no end at all. You get the idea. So that's the idea of circular cube. It's something like you have a set of processes. They're all waiting for some kind of resources. For example, let's see what type of thing. See, P0 is waiting for resources which is held by P1, process P1. P1 is waiting for the resources held by P2. P2 is waiting for the resources held by P3, and then P3 to P4, P4, P5, and then come back to P0. You get the idea? It's a circular resource. You get the idea? So this is a circular waiting. So because of these situations, deadlock occurs. These are the 4 situations why deadlock occurs. When there is a circular wait, deadlock occurs. When there is no preemption, deadlock occurs. When there is hold and wait, deadlock occurs. When there is a mutual exclusion, deadlock occurs. These are the 4 conditions. So all the 4 conditions must hold for a deadlock to occur. Okay. This one. Let's see the connection. Among the 4, the circular wait and the hold and wait are like kind of, they are like independent. Are like kind of independent means there's something different. Okay, not related, something like that. So this is one thing, the connection, you need to know the connection. Okay, so these are the 4 conditions why deadlock occurs. Okay, reason for the deadlock. Okay, then so let's see the deadlock in a pictorial form, in a kind of using picture. We call it resource allocation graph. When you see it in a graph, you will have a clear understanding. Okay, the resource allocation graph we are going to see. Graph means, don't think the graph in mathematics. It's a kind of picture. So graph here, it's a kind of picture. That's it. Okay. So the resource allocation graph. So here, deadlocks you are going to describe in terms of a graph. We call it a resource allocation graph. So here we are going to use some symbols. So symbols are vertices and edges. We are going to have some vertices, some edges. Okay. So here the vertices are for nodes. Node here means node here means the processes P1, P2, P3. So vertices here represents the processes. Okay, so remember, vertices represents the processes. Okay, and the resources, active processes in the system. It consists of certain resources. Okay, fine. Like so vertices here, it's going to represent the processes plus and the resources. So we are going to use the name P1, P2, P3, P4 for the process, and R1, R2, R3, R4 for the resources. So remember this notation. This notation I'm going to use. Okay, do you remember in the previous diagram when I was wait a second. When I was explaining before the previous slide, I draw one diagram. So the same diagram you just remember, you will have a directed edge. This was the one I was telling, the lines you write in between, it's a directed line. For example, let's say this is process P1. Let's assume this is P1. Okay, by the way, I'm so sorry about that. let me close it. Here we don't, I was using the rectangular sign for the process, is it? Actually, let's use the same symbol used in the textbook, circular symbol for the process. Okay, so P1 means it's a process. Let's assume that this P1 is holding a resource. So this symbol, circular symbol for process, like a rectangle or square for the resource. Okay, I was using other way around before. Okay, if you have a directed edge like that, okay, yeah, the directed edge. If you have a directed edge like this, it comes from resource, it's going to the process. The meaning is, this is the meaning. It's like the process P1 is to the resource type R1, then it is, the meaning is process P1 has requested an instance of the resource. Okay, so this is the idea of the okay, it means that, just a second, let me draw correctly. So you have a P1 and here you have R1. So this is the symbol, rectangular or square. So if the arrow goes like this, okay, direct from resource, not here, here, from resource to the process. So from resource to the process, the directed edge comes from resource to the process. That means the resource type has been allocated to the process. So this resource is assigned to this process. This is the meaning. Okay. Let's assume that if an arrow goes like this, let's say one more resource like this, R2, and the direction is like this. See it, the edge, the directed edge, where it is pointing the resource. Where it comes from P1. So it comes from the process and it's to the resource. Okay. So it's going to the resource comes from the process. That means the process is requesting the resource. P1 is requesting resource R2. Do you get the meaning of the edges and the vertices? So vertices represents the process and the resources. The edge in between, you draw some lines. In between the process and the resource, you draw the lines, is it? That is directed edge. Directed edge means there should be a direction, arrowhead. There should be an arrowhead. So where the arrow goes, there is a meaning. If the arrow goes to the process from the resource, that means this resource is assigned to the process. If the arrow comes from a process to the resource, that means this process is requesting the resource. You get the idea? You have to understand this this notation so that we can able to see the resource allocation graph. Where is it? Before, yeah, this is the graph. Yeah, before going to that, let's see that. Let's see some more things. Here I mentioned just 1 minute ago, I said that we will use this notation, circle, for the process and the resource, sorry, for the process. Circle notation for the process, and the rectangle or square, whatever, you know, the rectangle or square, it should be a rectangle, but sometimes we draw like a square also, fine, no problem. That is for the resource. Okay. And sometimes when okay, let me say one thing. So circle is for the process, fine, and let's have two processes, P1, P2. And the rectangle is for the resource. Let's call it R1. So this is the name of the resource. Sometimes you can have a notation called a dot. Okay, so let's assume this way. So what is the idea here? Let's see. I draw directed edge like this. Okay, let's draw this way. I can explain this one before going to the resource allocation graph. Can you see here? There is a dot. So we are using dot inside the rectangle. What is the dot means? Dot means one instance of the resource. Let's say the resource is a printer. Assume that resource mean it can be a printer, it can be a file, it can be a device, or it can be a anything else. Okay, it can be any hardware component, or it can be a software component like a file or a table or whatever. Okay, so let's assume that R1 here, it means R1. This resource R1 means a printer. So you may have more than one printer. You get the idea? So this is one instance of the printer. This is another instance of the printer. So can you see an arrow? Edge goes from this dot to P1. What does it mean? One instance of the resource R1 is assigned to P1. That is the meaning. So can you see the meaning of this line? Do you understand the meaning of this line? Okay, just a second. Okay, let's continue. The same thing, it got deleted. Let me draw it. So I was telling that we will be using some notations. Circle for the process, let's say P1. Let's assume there is one more process, P2, and you have a resource, certain resource. Let's say this is R1. R1 here means a printer. Sometimes we will be using a dot, not sometimes, always. Maybe one dot or two dots or three dot, it depends. Sometimes one dot, okay. Here the dot means instance of the resource, like one instance of the resource. Let's assume if you have the resource, three resource, so two instance or three instance of the resource. Sometimes we have like many output devices, printer, for example. So like three printers. So you have three dots. So when there is a line, edge, when there is an edge, okay, this is a dot, it doesn't look like a dot. Okay, fine. When there is an edge from the dot to the process like this, the arrow goes to the process. Means one instance of the resource is assigned to the process P1. This is the meaning. Sometimes there will be a directed edge from the process to the resource, not inside the dot. Okay, sometimes it's not, sometimes you will be having a directed edge from the process to the resource like this only. Don't go near to the dot, you stop here. Okay, so what is this meaning? P2 is requesting an instance of resource 1. It's just requesting, it's not at all assigned. Assigned means you will have a arrow from the dot to the process. Fine. This second directed edge, this means P2 is requesting a instance of the resource. Okay, it's requesting. Fine. So this is the idea of the edges that we are going to use in the directed graph. Let's see the directed graph in the next slide. This is the directed graph. Sorry, resource allocation graph. So this resource allocation graph, it shows a situation. What is the situation? It shows that we have certain number of processes, P1, P2, P3. So there are three processes, and there are certain number of resources, R1, R2, R3, R4. You see the dots here. See, for R1, there is one dot here. Can you see here? So here there is one dot. And R2 or R3 also has one dot. What does it mean? Only one instance of the resource. And for R2, there is two dots. So there is two instances of R2. And how about R4? There is three instances of R4. Okay. See, from the diagram, you just try to understand. One instance of R1 is assigned to P2. You see the line edge goes from the dot of R1 to P2. What does it mean? One instance of the resource is R1 is assigned to P2. Okay, And here also the same meaning. One instance of R3 is assigned to P3. Okay, here the same meaning. One instance of R2 is assigned to P1. One instance of R2 is assigned to P2. You understand the meaning, is it? This is another direction. You see another directed edge. There is an edge comes from P1 to R1. What does it mean? P1 is requesting one instance of R1. It's requesting. Okay, P1 is requesting. Also here, P2 is requesting R3. Also here. No, that's it. I'm sorry. That's it. Okay. So there is 2 requesting edges and 4 assignment edges. Okay, so 2 plus 4, you have 6 edges here. Okay then. So just understand that we have here resource instances. How many instances you have? For R1 you have 1 instance. For R2 also 2 instance. For R3 is 1 instance. And for R4 3 instance. Can you see here? 3 instance. They are not at all. Not until now. It's free. It's not assigned to any process. Okay, so this R4 is totally free. Nobody is using resource R4. This is one simple example of a resource allocation graph. Okay. So let's continue to see the same resource allocation graph. Whatever I explained before, it's the same thing given in the slide. Like process P1 is holding the resource R2. Process P1, this is process P1. It is holding one instance of resource R2. It is assigned to P1. Plus, it is waiting for an instance of R1. It is waiting. Can you see here? It is requesting. Not at all assigned. It's just requesting. So it's waiting for R1. This is the meaning. Waiting for R1. Okay. Same goes to P2. P2 is given one instance of R2. Plus it is waiting for R3. You see here, it is waiting for an instance of R3. How about the process P3? P3 just hold one instant. It is holding one instance of the resource R3. That's it. Okay. So from this diagram, okay, can you please tell me, okay, you understand the diagram, resource allocation graph. It shows you how many processes are there, what are the resources. You can see which resource is assigned to which process, which process is waiting for which resource. Everything is clearly given in this diagram. By seeing the diagram, any one of you tell me, among the 3 processes, which process will finish execution? Just tell this, seeing the diagram, can you please tell me, process P1, can it finish execution? Process P2, can it finish execution? Process P3, can it finish the execution? And can anyone tell me one answer? P3, super. Yeah. Because, can you see here? Process P3, here. Process P3 is given R3. P3 is not waiting for any resource. It is assigned with R3. So, it can finish the execution. Do you get the idea? Yeah. But after P3 finish the execution, I told you just a few minutes ago, I told you the resources will be released after the execution. So let's say P3 finish its execution. So the resource assigned to P1, sorry, who is this? P3, this will be free now. So there is no assignment. So it means R3, this resource is free. When it is free, this can be assigned to P2, right? This can be assigned to P2. After few seconds, P2 will finish the execution. Do you remember when a process finished the execution, it released the resources. So what resource it had? It had R2, so this one will be released. It had R1, this one will be released. You know, I'm erasing the line. I don't know how to erase, so I am crossing out. Okay. So now R1 is free. So if it is free, this can be assigned to P1. So P1 has R1, P1 has R2. So it has all the resources. So it can finish the execution and it will release all the resources. So P3 finish the execution first. After it releases, P2 will finish the execution. After it release the resource, lastly, P1 will P1 will finish the execution. The first one finish the execution is P3. Then it release the resource R3. That is given to P2. Then P2 will finish the execution. Then it will release the resource R1. R1 is needed by P1. So R1 is assigned to P1. P1 can finish now. Do you get the idea? Is it clear now? I hope you don't have any issues here. You understand the idea, is it? That's good. Remember, a process cannot finish its execution if it is waiting for a resource. If it is waiting for a resource, it will wait and wait and wait until it gets the resource. Once it gets the resource, it can complete the execution. Okay, remember that point. Okay, so we are still in the resource allocation graph. Let's see the resource allocation graph. Wait a second. Okay. Sometimes you may see some kind of cycles in the resource allocation graph. If there is no cycle, no process is deadlocked. If there is a cycle, deadlock exists. You see here, no cycle means no deadlock, no deadlock. If S cycle, S deadlock. Okay, so remember, if there is a cycle, that means you will have deadlock. Okay, so this is one kind of a simple clue. Okay, so if each resource type has exactly one reference, then a cycle implies that a deadlock occurs. If there is only one instance of a resource with the cycle, of course you can conclude that there is a deadlock. But if you have more than one instance, okay, so in that case, for example, if a cycle involves only a set of resource type, each of which has one single instance, then deadlock occurs. Okay then. But in case if there are several instances, so the cycle doesn't mean that there is a deadlock. Don't always think what I'm concluding here is, let's go back here. Just a few minutes ago, I said, if there is no cycle, no deadlock. If there is a cycle, there is a deadlock. This is the common definition. Okay. But remember that resources may have one instance or many instances. If there are many instances of a resource and there is a cycle, don't conclude there is a deadlock. Okay, because you have many instances. You get my point? Many instances means there's many dots. You see the rectangle sign, the symbol with the dots. That means many instances. So when there is many instances, who knows? There may be other instance that may be free. That can be assigned to the process. Okay. So a cycle with many instance resource doesn't mean that there is a deadlock. But cycle with where there is only one instances for the resources, then there is a deadlock. Okay. So this is the point I want to conclude. So that's the thing. Okay, so just understand this one instance and many instance. Okay, for example, I think I have a example for cycle. Here got a you see there are many cycles, not only one cycle. Okay, there is two cycles. Can you see here? Not only one cycle. So in this resource allocation graph, you can see two cycles. So there are two cycles here. Okay, let's see the meaning of it. You already know that the direction, the directed edge, P1 to R1. So this means that P1 is requesting R1. This means R1 is assigned to P2. This means P2 is requesting R3. This edge means R3 is assigned to P3. This edge means P3 is requesting R2. Here this edge R2, one instance of R2 is assigned to P2, and this means one instance of R2 is assigned to P1. Okay, so here you see kind of a deadlock here. So here let's see the idea first. Ignore this R4 because you have three instances, but none of the process is using it or requesting it. So ignore the R4 temporarily in this diagram. It doesn't have any purpose here. Can you see? No resource instance are currently available in this diagram. See, R1 has only one instance, it's assigned already. R3 has only one instance here, it is assigned, it's not available. R2 has two instances, also it is not available. Currently, none of the three resources are available, not available. Okay, so keep this point in mind. And can you see the request edge? Wait a minute. Where is the request edge? P1 to R1, P2 to R3, and P3 to R2. So these are the requesting edges. Okay. So we try to add a request P3 to R2, this one. So let's have a requesting edge P3 to R2. So here you will see the cycle. Let's see the cycle. The cycle is I'll start from P1. So here P1 to R1 and R1 to P2 and P2 to R3 and then R3 to P3 and P3 to R2 and then R2 to P1. Can you see the cycle? Cycle goes here and then here. Can you see the cycle here? It starts from P1 and it's end in the P1. That's a cycle here. Okay, one more cycle. Let's see one more cycle. P2 to R2, R2 to P3 and P3 to R2, R2 to P2. That's it. You start from P2 and you end in P2. Do you get the idea? So there are two cycles here. What is the meaning of this cycle? You see, P2 is assigned to R3. And sorry, P2 is requesting R3. But R3 is already been assigned to P3. Okay. But P3 is requesting R2. Where is R2 now? R2 is being assigned to P2. What is the meaning of this is process P2 wait for, this is the meaning, process P2 wait for R3 and process P3 is waiting for R2. Okay, this is R3. Is it R3? Okay, process P2 is waiting for R3. R3 will not be released. Why? Because P3 is holding it. P3 will release after the completion of the execution. But how come P3 will complete? Because it want R2. There is R2, it is with P2. P2 will not finish because it want R3. Where is R3? It is with P3. Do you get the idea? So this is the thing. For example, I hold your resource and you hold my resource. So it's like mutually we are like waiting for each other. Do you get the idea? So this is a kind of a deadlock. I can't release because I didn't finish. I need a resource that you hold. And you can't finish because you need a resource that I hold. This is the deadlock situation. Do you get the idea? Everybody, is it clear with you all? Is it clear? This cycle here represents somebody is holding somebody else's resource. And they are waiting for the others. The other is holding the others. So can you get the idea? So something like it goes in a loop and one holds something and one waits for something. Okay. The waiting for something is already in hold and they cannot finish. If they finish, yeah, of course, I can understand that. Is it clear with you all? So this is the idea of deadlocks, and that you can see it from this graph. What is a deadlock here? Okay, fine. This resource allocation graph clearly it tells you that what are the processes, what are the resources, how many instances are there for each resource, and which process is holding a resource, which process is requesting a resource. All these details you can see it in the resource allocation graph. Fine. I think you don't have a doubt. Hopefully. Okay, then let's continue with the some more example of the resource allocation graph. So let's see this graph. Okay, so you can see very clearly the cycle. Is the cycle? Anyone can tell me? It's written in the diagram. Okay, otherwise you can write it. Never mind. So you can see a cycle in this graph. Here it is. P1 request R1. This R1 is with P3. P3 request R2. This R2 is with P1. So you clearly see a cycle. So this is the cycle here. You start from P1 and you end with P1. So this is the idea of a cycle. If you remember, just a few minutes ago, I told you, where is it? Yeah, a few minutes ago, I told you that if there is, where is it? If there are several instances, maybe there is a cycle. You see a cycle in the resource allocation graph, but there is no deadlock. Okay. Don't think that cycle means deadlock. Okay, yeah, cycle tells you there is a deadlock, but if there are many instances of a resource, then probably cycle is not a deadlock. Okay, so that is the example here. Here, in the previous thing, of course, we see a deadlock. Even though R2 is having two instances, still you see a deadlock in this resource allocation graph. Here is a deadlock, but here there is a cycle. Okay, this is the cycle. One is requesting R1, R1 is assigned to P3, P3 is requesting R2, R2 is assigned to P1. So you see a cycle here, but there is no deadlock. Here it is. There is no deadlock. Why? Let's see. Can you see here there is another instance of a resource R1? And there is one more instance of a resource here R2. Okay, that R1 is already assigned to P2. So this process P2 doesn't need any more resource. So P2 can finish the execution. If it finishes the execution, it will release the resource. If P2 release the resource, that can be assigned to P1. Do you get the idea? Similarly, there is one more instance of R2. It's assigned to P4. Yeah, fine. So P4 doesn't need anything else. So it can finish execution. When it finish execution, it can release the resource. So this resource, another instance will be free. So that another instance can be assigned to P3. So P3 can finish its execution. Do you get the idea? So this is the idea of, you see a cycle, but there is no deadlock here because there got some other instances of the resource that can help you to fix the problem. Okay, so here it is. If there is a cycle, the system may or may not be in deadlock situation. Okay then, so may or may not. So cycle means there may be a deadlock, there may not be a deadlock. Okay, how? Depends on the other instances. So the other instance of the resource can help to fix the deadlock. Okay, it will, the other instance will break the cycle. So that's the idea here. See, the other instances of the resources may break the cycle. If the cycle is broken, there is no deadlock. Okay, you get the idea? So you need to understand this. If there is a cycle, there may be a deadlock, there may not be a deadlock. So that point you need to remember it. And handling the deadlock. So how are we going to handle the deadlock? So there are 3 ways to handle the deadlock problem. So we can use the, wait a second, we can use protocol to prevent or avoid the deadlock. We use a certain type of protocols, okay. And we can allow the system to enter a deadlocked state and then detect it and then you recover it. So the system has to detect there is a deadlock and then it has to recover it, okay. Or ignore the problem altogether and pretend that deadlock never occur in the system. So this is the thing there are 3 ways to deal with the deadlock situation. So you can use some protocols to prevent the deadlock or avoid the deadlock, or you can use the system, you make the system to identify there is a deadlock and then recover from the deadlock. Just pretend that our operating system doesn't doesn't support deadlock. I mean to say doesn't this current situation may not lead to deadlock, something like that. Pretend that deadlock may not happen, something like that, okay. So the third solution, that is pretending the deadlock never occur in the system. So this third solution is the one used by most of the operating systems, like the one we normally use, Linux, Windows, etc., etc. So it's up to the application developer to write a program that to handle the deadlocks. That one we will see in the next topic, how to prevent a deadlock. Okay, that is the next topics. Sorry, just a second. Okay, so for example, let's say that if you want to make sure that deadlock will not happen, so either the system, you need to have the system to use either a deadlock prevention or deadlock avoidance scheme. If your operating system uses a deadlock prevention technique or deadlock avoiding technique, of course you won't have deadlocks in your system. So here, deadlock prevention, it provides a set of methods to ensure that at least one of the necessary condition cannot hold. You know the conditions we saw the beginning of the slide, mutual exclusion, hold and wait, those, no preemption, the 4 set conditions. So the deadlock prevention makes sure that one of the condition cannot hold, okay. So at one of the if any one of the condition occurs, this deadlock. Is it? Okay then. So these methods prevent deadlock by constraining how requests for the resources can be made. Okay then, so we will see the prevention after a while. So preventing deadlock is going to be a topic. Just wait for a while. Now let's see the deadlock avoidance. Just now I say that either the operating system needs to have either the deadlock prevention technique or deadlock avoiding technique. So here in deadlock avoiding technique, it requires the OS to be given additional information in advance. Regarding what? Regarding which resource the process will request and it's going to use during its lifetime. For example, I'm going to have a process P1 and P2. So I'm going to execute this process. I'm going to execute P1 and P2. So operating system needs to have some information about P1 and about P2. What information? So this P1, what are the resources it's going to use for the execution? So for the execution, P1 wants what are the resources. So if I know those details, we can avoid the deadlock. How? We can keep those resources ready for the execution of P1. Do you get the idea? So if these additional knowledge is there, deadlock can be avoided. So with this additional knowledge, operating system can decide each request whether or not the process should wait, something like that. Okay. Decide whether the current request can be satisfied or it has to be delayed. Can you get the idea? Must consider the resource currently available. Can you see that one? If we know some details about the processes, so the operating system can able to avoid the deadlock situations because it knows the future request. So if you know the future request, so the deadlock avoiding can be done. Okay, because we know what are the resources the process is going to request. Do you get the idea? So we can make sure that that resources may be made available for the resource, or the request can be delayed, whatever. Okay, this is about the avoiding. So not yeah, that's avoiding and prevention. This is the how to handle deadlock. There are 3 techniques, and among the 3 techniques I'm talking about the first technique. Okay, for example, if a system doesn't employ either prevention or avoidance algorithm, let's assume my operating system doesn't have the prevention technique or avoidance technique, so of course you will have the deadlock. You will end up with this deadlock. So in this environment, system can provide an algorithm that examines the state of the system to determine whether the deadlock occurred or not. So if there is a deadlock occurred, so the algorithm to recover from the deadlock. If there is a deadlock, it can be recovered from the deadlock. This is the second situation, and the second technique. Do you get the idea? I was telling 3 techniques before, quite a few minutes ago. There were, wait a second, where is it? There were 3 ways to avoid a deadlock. These are the 3 techniques to avoid deadlock. So the third solution is the one most of the current operating systems are using. And the first technique we are going to see after a while, preventing deadlock. We have a topic for deadlock prevention and deadlock avoidance. Okay, we have a separate topic. And this next one, the second one is, so we need to have the OS to have certain type of algorithms. Okay, so it needs to have some kind of algorithm to examine whether the current state of the system is a deadlock situation. Then it needs to have an algorithm to recover from the deadlock.